Kevin Laeufer from UC Berkeley.
Hello. So yeah, I'm a student at UC Berkeley. I'm working programming languages and hardware. And I had this little project where I was trying to understand how guarded atomic actions work. Guarded atomic actions are an abstraction for RTL design that was developed at MIT in the early 2000s. And what I did is I sort of have a prototype implementation that is built on top of Chisel, and it allows you to describe single module guarded atomic action, single guarded atomic action modules, and there's some flexibility in the scheduling, and I think this is an interesting example to sort of show what kind of things you can easily build on top of Chisel and where the limits are. And so if you're interested in this, come and find me at the poster session. Just to explain to you what's on my slide, it's the hello world of hardware, which was previously mentioned, which is the GCD circuit. And on the left side is the classic description that I took from a BlueSpec slide. And on the right is sort of what it looks like on top of Chisel. And you see it's a little more noisy because we don't have our own parser. We're just building that in Scala. But it actually sort of matches line by line. So come talk to me.
Next up is Richard Lynn, and on deck is Derek Chou and Richard Lynn.
Okay, it's just a Google slide. All right, so we've all heard the usual advice for chip development: test well and test often. That you want to catch all your bugs in pre-silicon, right? But forget about being proactive. I'm here to make debugging great again. Okay, more seriously, maybe there's some people who actually don't believe in process or think that they can't possibly make mistakes, but it's still obviously better to fix bugs before they're quite literally set in stone. But the reality is that you can't catch everything through only testing and simulation. And compared to the massive verification resources available to industry, research groups are usually very focused on one problem, and they lack the will and manpower to implement standardized protocols like JTAG or reusable infrastructure for on-chip visibility. In fact, legends tell us of battle-hardened students turning away from the complexity of the 400-page JTAG spec in horror, vowing to write their own dead simple scan chain. Instead, what actually happens is that this just pushes more work to when their chip comes back. Now you have to write custom software to interface with your custom debug port, not to mention the potential correctness issues of this one-of roll-your-own solution. And if we aren't willing to debug good transports, there's the even more complex infrastructure for debug visibility is basically a non-starter. Anyone who's debugged knows that visibility is key, and blind debugging leads to fun, time-intensive strategies like let's randomly poke bits until it works. And without tools like an on-chip logic analyzer backed by fast memory, your only real alternative is breaking out internal buses to pins. Some of you might argue, but chip scope and synthesis tools and JTAG scan chain insertion or vendor high-speed trace IPs. Problem is, those take time to learn, and that investment in learning might not pay off consistently across simulation, FPGA, and tape-out. So my hunch is that good debugging blocks is infrastructure that everyone wants to use. If only someone else would write it and provide a clean, intuitive API with readable documentation. If you could write a JTAG port, boundary scan shim, and built-in logic analyzer with a few lines of Chisel to connect everything up, wouldn't you use it too? If you're interested, come check out my poster. Take a look at how the interface works, and let me know your thoughts on how we can make debugging great again. Okay, and then I have another poster. Sorry, this one won't be quite as entertaining in the same way. Okay, so completely changing gears. While much of the work done in Chisel involves novel processors and complex accelerators, here's a different application. Here at Berkeley, we have a variety of engineering project teams. One of these designs, builds, and races solar electric cars, like the one you see up there. And for those of you not familiar with electric vehicle architecture, they usually have a battery pack consisting of a series connection of parallel groups of individual battery cells. And as individual cells charge and discharge, their voltages drift from one another and become unbalanced. And as this pack is limited by the weakest link, typically the lowest voltage in the pack, imbalance results in cells reaching the shut-off limits while there's still energy left in the rest of the pack. Active balancing addresses this by shifting charge between cells, keeping everyone at a uniform voltage. The active balancing system we implemented consists of a power stage controlled by PWM generators on an ICE40 FPGA, selected for its ease of use and the existence of the fully open source Yosis toolchain. These are controlled by a microcontroller, which makes active balancing decisions based on sensor data from the rest of the vehicle, communicating through an SPI link, and all the RTL we built in Chisel. During development, use of Chisel provided many advantages over conventional languages. Of note is agility. The use of parameterization allowed us to test on pre-existing ICE40-based hardware before the active balancing electronics arrived, which is a crucial requirement for your typical last-minute, highly agile student projects. And deploying non-production hardware later just became a matter of changing some numbers. Furthermore, a functional programming approach allowed an extremely concise specification of repeat and complex logic, while generators allowed automatic computation of constants such as for CRC. Chisel's testing infrastructure made unit testing easy and natural, which became critical for detecting regressions while rapidly iterating, because when you're dealing with serious power electronics and high energy density systems, you really don't want your RTL mistakes starting a fire. And during our 3 days at the track qualifier and 9 days on the Oregon Trail route through the 2018 American Solar Challenge, the active balancing system kept our battery cell voltages within 0.5% of each other, contributing to our all-solar finish. The reliability is especially impressive considering the nature of this project, started and completed in a short month leading up to the race. So if you're interested in learning more about Chisel in embedded automotive or power applications, come check out my poster.
So I'm actually going to give the Dongyi's presentation. He couldn't be here today because of other commitments. His poster is about RISC-V Mini, an intermediate example of Chisel. Why do we need more examples? Well, we have some very simple designs, and then we have Rocket Chip. And this is an attempt to bridge the gap between those two extremes. This was developed for a class project, and there were several goals. One was to learn about Chisel and to learn about Rocket Chip, and then also to have a design that was complex and yet simple enough that it allowed development of further downstream tools. So you could learn how to write pipeline data paths, how to write table-based decode logic, how to write caches with finite state machines, how to write unit tests, and how to integrate all this together into a single project. What about research? Well, RISC-V Mini, while we were developing Chisel 3 and Fertile, it provided an environment where we could verify that at least moderately complex projects could make it through. It's also simple enough that it's very fast to simulate, both in FPGAs and in Verilator. It uses the same tool chain that the major Rocket Chip repo uses for developing code to run on the processor. So it leverages off all the work that's gone into that repository. We're suggesting people use it as a way to understand a relatively complex processor and learn about Chisel and how to integrate design and testing. And we're inviting people to make contributions to it, keeping in mind that the goal is to have something that's simple enough that it can be implemented and simulated in a relatively short amount of time. And now Adam's.
Great. So I'm My poster is on chisel/fertile intervals for bit width reduction. So the motivation for this, the work was we were writing a chisel DSP library for making DSP chisel circuits, and we wanted to make them as parameterized as possible, and that meant including a lot of things for data type parameterization and operator behavior parameterization, and making our testing infrastructure sort of unified for all of these different parameters. Just parameters, parameters, parameters. But the other thing that we wanted to unlock were unobtrusive optimizations. So we wanted to do automatically do bit reduction techniques that a lot of DSP designers do manually in industry. So our solution to this problem was to add a new chisel and fertile data type called interval. And the idea of this is you don't think of wires as having a set of bits, or some like bit width. Instead, it represents a number within a range. And because if you do that, then you know what the possible max and minimum value can be. You can do better with inference later on because you don't have to always be conservative about it. And you can also still guarantee the correct result. So if you do this properly, then you'll get only area reduction in area with no change in the actual behavior of the circuit. So this is an example, maybe I can make it a little bigger there, of what it looks like in Chisel. It's currently on a branch and will be PR'd soon. We're working to get it merged into master, fully upstreamed. But it looks something like this, where you can declare the range of what your interval type is, and then everything just sort of works as normal. And you can write tests and et cetera. So it's basically just another data type. The actual implementation was tricky. So if you're interested in the changes to the Fertile compiler, there were some and a lot of thinking about how this would work. So if you're interested, you can definitely come talk to me about that. The other part of this work that we were doing was there are some applications where you know exactly what your input set is, or you know what the distribution of your input set is. And so you can do additional sort of dynamic profile-driven bit width optimizations. So you put in a test vector and you figure out, you sort of bin what the possible values a wire could have, and then you can trim the widths with that information. So, and here we have a sort of, after running with profiling information, you can see a histogram of what all the possible values were on different wires, and then you can do additional area reduction based off of that. We have some area results, and basically showed that in general, you reduce area by a nice amount with no effect on performance. All you have to do is use the interval data type. There were some cases where the synthesis results were larger, and the reason for that is, well, we're not quite sure, but we think it's because there are some quirks in the synthesis tool, and that this is within the noise, but yeah, so we're not quite sure. So the other thing is this was sort of our first attempt at building a whole new fully supported ecosystem on top of Chisel in the DSP land. So we have a lot of thoughts on how you design libraries and when, and hopefully this information can be helpful to other people here who are thinking about writing their own Chisel library. So please come talk to us if that's interesting to you. Thank you.
Hi there, my name is Nima Ganjalu, and today I'd like to talk to you about integrating cycle-accurate Chisel models into the Gem5 architectural simulator. And what really got us thinking about this in the first place was the rapid rise in popularity of the RISC-V ISA. There were quite a number of interesting and complex developments coming out of that, and we wanted to see what we could do to help accelerate those developments. And we decided that Gem5 and Chisel was the best route for that. And before I continue, just a little bit of history. background, Gem5 is a cycle level simulator, which basically means that the models it uses mimic the hardware, but don't necessarily represent the actual implementation of the hardware accurately. And so you can think of that as a high-level emulation. And on the flip side, you have a cycle-accurate simulator, which basically does represent the hardware implementation fairly accurately, and that's where Chisel comes into play. You define a piece of hardware in Chisel, and then at some point generate a cycle-accurate C++ model of that hardware using Verilator. And the idea there is, if you had some sort of system with a number of components, CPU, GPU, memory, an accelerator of some sort, you'd like to be able to choose the components that you want to do a detailed analysis of without doing a detailed analysis of the whole system, and just generate a cycle-accurate model for that particular component, and then model the rest on a high level. And so what we did for our initial design is take the Sodor RISC-V CPU core and generate a cycle-accurate model of the core itself, and then model the memory in Gem5, and had a wrapper between those two models to communicate and run some simulations. And we're thinking about adding a fertile interpreter as an alternative to the cycle-accurate model at some point in the future on top of some other types of models. And we have a number of questions for the community here, so we'd love to see you at our poster and talk to you. Thank you.
Okay, hello everyone. We present a case study of using a pre-existing Chisel design in a traditional Verilog top digital SoC design. The pre-existing module was a GFSK modulator, a digital circuit used to control the frequency selection bits of a digitally controlled RF oscillator, which in turn generates an output frequency spectrum. The module was parameterized for a number of different variables, including input data frequency, module clock frequencies, modulation shape, and a number of output control bits. These generator parameters made it straightforward to specialize for the new designs. We also added framework for the supporting elements around the module, such as FIFOs, clocks, and MUX configurations. Additionally, the new design required a unique naming convention for modules to be integrated into a Verilog top to avoid potential conflicts with other modules, which were themselves all written in Verilog. To resolve this, we used a fertile renaming pass to rename the Chisel-generated Verilog and all submodules to comply with the naming convention. Finally, to build supporting test instances around the module, we used clock wrappers to generate phased and different frequencies of clocks, which can also be reused in future projects. Future improvements to Chisel could include better multi-clock testing support, as well as more fine-tuned control of the outputs generated by Chisel. Feel free to come talk to us at our poster if you'd like to learn more about this. Thank you.
Hi everyone, my name is Edward, and today I'll be presenting a poster about the tape-out class. So Professor Christopher Piester and I offered a class unique opportunity to allow undergrads to tape out a Bluetooth SoC, including analog, digital, and RF components, and with a team of undergraduate students who have never taped out before. So as many of you in this room know, SoC design is extremely complex, so the question was, how do we make the best use of this unique opportunity? So if you just wanted to learn analog or digital design, there are classes available for that, but this class is unique because students get to assemble and build the entire SoC. So there's kind of two ways to make use of this, to make this challenge more tractable. The first is to provide a pre-built SoC that the students then modify, but I think that misses the most unique aspects of this opportunity, being able to design, think, and assemble at a system level instead of micro-optimizing the specifications for one block. And the other option, of course, is to build everything full custom, but that's also very time-consuming, so not practical. So I think that generators are the solution to this conundrum. So the solution is to the solution involving generators has two main benefits. The first benefit is to if we leverage existing generators at the system level, that provides us with flexibility. So if we need to change specifications, we don't have to redo a lot of designs. And generators can also allow students to build their own contributions and designs much faster. So if you're interested in finding more about what happened to this project, come talk to us at the poster. Hi, it's Edward again, and this is the second poster. Yeah, so as, again, you've all heard the talk, heard Chisel and Fertile being mentioned many, many times today, so I won't belabor the point. So they make it possible for us to rapidly explore designs, but as soon as the rubber hits the road of physical design, we suddenly have an issue of lack of reusability. So we have Chisel, that's a Chisel that enables parameterized Verilog. We have Fertile that is a more robust and principled approach than Perl scripts, but what are the approaches that we have to replace the current physical design methodology? So Hammer is a new physical design generator project that we started at Berkeley that is intended to extend the hardware generator chain so that when the rubber hits the road, we don't run into the desert and we can achieve the goal of tape out. So come speak to us at our poster. Thank you.
Hey, my name is Hassan Gench, and I'm a new student here. And I have a poster on a new feature that we're adding to Chisel, strong, safely typed enums. So why were we interested in replacing the old Chisel enums? The old ones were lacking certain features that people expect in other languages. They were unsafe. They could be freely connected to other Chisel data types, which can cause certain bugs. They wouldn't preserve their type information going down into Fertile, so HDL backends or waveform viewers and stuff couldn't make use of them. And this led to some fragmentation in the code base where different projects would just ignore the Chisel enums and make their own implementations. So to kind of unify them all together, we're proposing a new API, which has already been pushed upstream. So if you guys want, you can play with it. And we base it on our analysis of other enums in other languages for both hardware and software. So just to give a quick preview, this is basically it. It's pretty self-explanatory, I think. You create your own enum type, which I called my enum. You can give it default values, or you can give it custom values if you want, mapping to different unsigned integers. And the nice thing is it looks pretty much exactly like the built-in Scala enumerations. So there should be minimal friction between the two. And you can use it exactly the same way that you would use any other Chisel data type. You can use it to create registers. You can connect those registers to the values that you just declared, whatever you expect. So each of these enums is a different, unique Chisel type. So you can't connect them to Unums. You can't connect them to each other if they're not the same kind of enum. You can't compare them, et cetera, et cetera. We use the annotations that Skylar talked about earlier to preserve their type information going down into Fertile. So in the future, we're probably going to have waveform viewers that can read these annotations and print out the actual names of your enums instead of just their integer values. And if people want to get around the type safety, we allow them to typecast to any other Chisel data type that they want, or from a Chisel data type back to an enum, although that can sometimes be unsafe. So if you guys have questions, suggestions, scathing criticisms, come talk to me at the poster. Thank you.
And I believe that is all of our posters. So let's give every presenter a round of applause. We will continue with the poster session in the Great Hall, I think it's called. It's just down the hall. And I believe food will be there as well. And oh, there is a bar, but it is a cash bar, which means you have to pay for it, but they don't accept cash. They only accept debit cards or credit cards. So, yeah.